Hi, good morning, everybody. So the last class, we I think stopped somewhere here. We began with a linear dynamical system, x dot equal to ax, and then towards the end, we looked at a two-dimensional version of it, where a is given by a, b, c, d. It has four entries a, b, c, d. Then we expressed the characteristic equation in terms of the trace and determinant. Trace is the sum of all the diagonal terms, that is a plus d, and determinant is ad minus bc. So if you express the roots of the system in terms of trace and determinant, so like these are the eigenvalues of the matrix A, then we can classify the fixed point that you get in terms of this eigenvalue. You have done the classification before. That is, if both are negative, both are positive, one positive, one negative, and so on. So you can, this is simply your +2 quadratic equations in a topic. If you work this out, you basically get this plot. That is, as you vary your delta determinant and the trace tau, you get different kinds of fixed points, different kinds of dynamics, right? And as you continuously move in the space of delta tau, at certain critical values, certain critical boundaries, your dynamic suddenly changes. So what was a stable spiral suddenly becomes unstable, and what was unstable spiral suddenly becomes unstable node, and so on and so forth. So such sudden changes in dynamics is called a bifurcation, and therefore this picture shows all possible bifurcations that can occur in a linear two-dimensional system expressed as a function of delta and tau. So therefore, such maps are called bifurcation maps. This is for a very simple system, but you can do the same thing for more complicated cases. So now with this, let us look at a very funny example, which is given in Stockard's book. I hope you are looking at the Stockard's book because all the dynamical systems part I'm taking from that book. So this problem that he poses is like this. So it's about Romeo and Juliet. So Romeo is in love with Juliet, but in our version of this story, Juliet is a fickle lover. The more Romeo loves her, the more Juliet wants to run away and hide. But when Romeo gets discouraged and backs off, Juliet begins to find him strangely attractive. So it's kind of a strange character. So Romeo, on the other hand, tends to echo her. He warms up when she loves him and grows cold when she hates him. So Romeo's behavior is very simple. If she is positive, he is also positive. If she is negative, he is also negative. Whereas Juliet is opposite. If he is positive, she is negative, and if he is negative, she is positive. I mean, to put it in mathematical terms. So the question now is, how do you describe their interaction? How do you describe their emotional dynamics? Right. So the answer is like this. So let R and J be represent the emotional state of these people, Romeo and Juliet, respectively. Positive means love and negative means hate, something like that. All right. Therefore, so since R very simply directly as a function of J, that is, if J is positive, R increases. J is negative, R decreases. Therefore, R dynamics can be represented as R dot is equal to AJ, where A is positive. Since Juliet has opposite behavior, all right, so dj by dt is equal to minus b r, where b is also positive. So this is a very simple description of the dynamics. Now, if you write down the equation, so if you write it in the form x dot equal to ax, where a is a matrix that determines dynamics, here a becomes 0a minus b 0. All right. So if you solve for it and find the eigenvalues, you find that lambda is equal to plus or minus I times square root of AB. So where I is the imaginary number. So in this case, both the eigenvalues are imaginary values. Or purely imaginary numbers. So we know that in case of purely imaginary numbers, the fixed point that you get is called a center. Right. What that means is solution is of the form some kind of a cos omega t plus b sin omega t, something like that. It's a pure oscillation. Both x and y are pure sinusoids. So if you plot one against the other, you will get an ellipse, right? Because amplitudes are likely to be different in general, so you get an ellipse. And so what that means is, when R is fully positive, J is 0, and when J is fully positive, R is 0, and so on. So they are never in sync. They are constantly out of sync. So Stogards described this as a never-ending saga of love and hate, which is quite a sad story. Right. Then in the book, he also takes a more general case where R dot is equal to some AR plus BJ and J dot is equal to some BR plus AJ. So slightly more complicated dynamics, and what are all the kinds of behaviors you see, and so on and so forth. The thing is, it looks like a funny example, but people actually write down differential equations to describe family dynamics, right? Social dynamics and things like that. So it's a very simple example that can give us some insight into social dynamics. Okay, so with that background, let us go to a slightly more complicated situation. Complicated in one sense and simpler in another sense, right? We'll look at the dynamics of a system which is nonlinear, right? But in two dimensions. So until now, we have seen the general linear system, x dot equal to ax in n dimensions, right? Which is very simple. Once you solve it, you know the effect of eigenvalues on the fixed point, and there ends the matter. There's nothing more to understand. But the moment you go to nonlinear systems, I mean, it's literally whole hell breaks loose because there's no general solution or the general way of characterizing and defining and understanding how it works. Every system is different, right? So you can only give some general tools to approach the study of nonlinear dynamical systems, right? And one such tool is phase plan analysis. So this is a kind of analysis that is applicable to two-dimensional general nonlinear systems. Generally, they are nonlinear. You can also apply it to linear, but it's trivial, right? Why do we want to study it in two dimensions? The several advantages. One is you can easily visualize. You can draw pictures. You can draw a graph of x versus y and see what is going on in the plot. And another thing is interesting thing is even a two-dimensional system, if it is nonlinear, can have very rich dynamics. So that itself is a huge field of study before you even go to higher dimensions. Particularly a kind of dynamics called limit cycle behavior, which is a special kind of periodic behavior, right, can be captured using even two-dimensional systems. And that is quite relevant for us, for understanding of neuron models and all that. So we'll see why it is, right? But disadvantage is that in a two-dimensional continuous dynamical system, you cannot get chaos. A special kind of a dynamical behavior called chaos. You cannot get it in a two-dimensional continuous dynamical system. That's okay. So in this course, we are not looking at chaos. So we are okay for now. So how do you study that? What is the general form of a two-dimensional nonlinear dynamical system? So it is given like this: the two variables x and y. So earlier we were using notation x1, x2, x3, xi, right? But now for the phase plane, let's use notation x and y. So the x dot is equal to f of x comma y dot equal to g of x comma y. So this is a very general form of two-dimensional dynamical system. Now, how do you study this? So first of all, the very first thing that you do is to find out where these functions go to zero. First of all, where does x dot go to zero? Where does y dot go to zero? Right, and then you plot it in the phase plane. That's why you need a. That's why you call it a phase plane. That is because you can make these plots in two dimensions. Now, the plot of f of xy equal to 0 is called the x null plane, and the plot of g of xy equal to 0 is called a y null plane. Cline is some kind of a line. Null is 0, so it's a line where x dot becomes 0. So this is just a schematic of that. Suppose I have two functions, f of xy looks like this, and then g of xy looks like this. It can be any curve, right? And so this curve is called f of xy equal to 0 is called this is x null plane. And g of xy equal to 0, this is called the y null plane. And in this picture, you can see that the two intersect at 2 points. So these are the fixed points because at these points, both of them become 0. Okay, now how do you study them? What is the dynamics of system? How do you study them? One simple trick that people always consistently use is to first find out the fixed points where both these curves meet. That means both functions become 0 simultaneously. And then, so study the dynamics around those fixed points by linearizing them. So how do you do that? So let x be equal to x naught plus epsilon x, and y be equal to y naught plus epsilon y, where x naught y naught is a fixed point. Then you can expand this function, right? Say around x0 and y0. F you can expand around x0 and y0 like this. So epsilon x dot is equal to f of x0 y0 plus epsilon x into dou by dou x plus epsilon y into dou by dou y plus higher order terms. Similarly, for epsilon y dot, you get g of x dot y dot plus epsilon x gx by dou g by dou x plus epsilon y dou g by dou y plus higher order terms. Now we know that since x0 y0 is a fixed point, right? Both f of x0 y0 and g of x0 y0 both become 0. So you get, and then you ignore the higher order terms. So you get something like this. This equation is your similar, your familiar linear dynamical system form, like x dot equal to ax, right? And this is valid in the neighborhood of the fixed point x0 y0. So this matrix is called the Jacobian. Right, you can, in a more compact form, you can write it as epsilon dot is equal to j epsilon. Okay, so you can do eigenvalue analysis, you can find out eigenvalues and find out what kind of fixed point it is and so on and so forth. So this is something that's standard. So now let us apply this to see how we can understand a dynamical system, right, by following this procedure. The procedure is, given the system, first draw the null lines, find the fixed points, linearize the system around the fixed points, understand type of stability, and with this knowledge, can you find out how the dynamical system works? What that means is, can you find out the entire vector field of the dynamical system? So that means if you start from some point, where do you go? How do you progress? Right? What's your trajectory? That's what we want to understand. So let us see that in this simple example. So this equation system is given by two equations. Dx by dt is equal to minus x plus x cube. Dy by dt is given by minus 2y. Okay, so how do you solve this and how do you do the phase plane analysis? Like I said, first thing is you find x null plane. X null plane is given by dx by dt is equal to f of x comma y is equal to 0. That means minus x plus x cube is equal to 0. Now this is supposed to be actually a function of both x and y. But in this case, it's a very simple example, right? This expression happens to be only a function of x. And when you solve it, you get x equal to 0, 1 or minus 1. Right? What does it mean? What about y? So y, since y is not even there in the expression, it means y could be anything. So the solution in this case for the equation f of x comma y equal to 0 means x equal to 0, 1 or minus 1. Y is anything. Y is anything in the vertical axis. So similarly for the second null line, the y null line, if you solve g of x comma y equal to 0, so g of x comma y is minus 2y. You set it to 0, y is 0. Therefore, x is anything. It can be so entire x-axis. So y is 0, x is anything. So let us plot this. The x null lines are, there are three lines. X is 0, 1 and minus 1, y could be anything. So that gives you basically three vertical lines. X is minus 1, y is anything, this line. X is 0, y is anything, this line. X is 1, y is anything, this line. Okay, that is the three lines together form the x null line. Similarly, if you take g of x comma y, y is 0, that is y is 0, x is anything, that is obviously the x-axis itself. So these three form the x null plane or x null planes. The x-axis is the y null plane. Now, where do they intersect? At 3 points. So you have 3 fixed points. So now we need to find out their stability. So how do you do that? Find the Jacobian. So basically take this system and differentiate around a fixed point. So in general, the derivative of this, that expression will be like this. Minus 1 plus 3x squared, 0, 0, minus 2. Now, if you plug in the fixed point values, that is at the origin 0, 0, we find A is equal to this, which means eigenvalues are minus 1, minus 2. So both are negative and real. Therefore, it's a stable node. So origin is a stable node. And the other 2 points, that is plus or minus 1, that is these 2 points, plus this minus 1, 0 and 1, 0, that is plus or minus 1, 0. If you plug these values in this expression, you get A, in both cases, you get A equal to 2, 0, 0, minus 2. Eigenvalues are obviously 2 and minus 2. So here we have saddle nodes. Okay, so now what we know is, so we know that these are the x null plane, this is the y null plane, these are the fixed points, and this is a stable node, and these two are saddle nodes. Here you can also find out, that see, in this case, lambda 1 is 2, and that is positive, lambda 2 is negative. So therefore, the x dimension, right, is unstable, y dimension is stable. So that means on the x dimension, if you kick it off this point, it will move away, right, from the fixed point. And the y dimension is stable because eigenvalue is negative. If you kick it off this point, it will come back to that point. So you see that's a saddle node. It attracts in the vertical direction and repels in the horizontal direction. So now from this, can we find out what happens if you go off the axis? Maybe if you start from here. So you can see that, right, when you are here, there is a vertical force acting downwards and a horizontal force acting rightwards. So if you are here, you will move like this. So generally, so the trajectory of a point here, right, will be something like that if you are in this quadrant. So similarly, if you are here, there's a vertical force acting downwards, then there's horizontal force acting leftwards. So if you are here, you will go like this. And when you are here, there is a vertical force acting upwards. There is a horizontal force acting leftwards. So you will go like this. So similarly, you can argue that you can go like this. So around this saddle node, you can see that what this is called the flow, right? The flow of the vector field, right? Looks like this. In this quadrant, you will move like this. In this quadrant, you will move like this, like here like this, and here like this. So this is how the flow is in the neighborhood of this fixed point. So this is how you understand how the flow of the dynamical system is by taking the fixed points as some kind of centers, as some kind of a coordinating centers. Once you understand the behavior in the neighborhood of the fixed point, you can extend it to find out, right, how it is in slightly far off neighborhood. So similarly, let us take the origin. So origin is a stable node. So this attracts flow in all directions, horizontally towards it, vertically towards it. Okay, so it's everything moves towards it. So this is how it looks. Now again, when you go to the other fixed point, which is again a saddle node, in the vertical direction, it attracts, horizontal direction it repels. So it looks like this, very similar to this. And now you can also verify that these three are consistent, because this chap is pushing the flow away towards the right when you are on the right side. This fellow is attracting the flow towards itself when you are to the left of it, and both are consistent, right? So if you find yourself somewhere here in this strip, this guy pushes you away, this guy attracts you, and you will end up here. So similarly, if you find yourself somewhere here, this fellow pushes you, this fellow attracts you, and you find yourself somewhere here. So what these methods tell you is, when you have a dynamical system in 2 dimensions, right? Because phase plan is only for 2 dimensions, right? You first find out the null lines, then find out the stable points, and find out the fixed points, find their stability, and understand the flow in the neighborhood of the fixed points. With that, you can extrapolate and find out how the flow is all over the plane. Okay, this is the overall approach. Things can get a lot more complicated than this. This is a very simple example. So, but that gives some idea of how it works. Okay. So now what I'll do is so go to a certain website, right, just to show. So can you all see this website?
Yes, sir.
Yeah, so this is a website for plotting implicit functions, right? Anybody knows what an implicit function is? Hello, anybody? What is an implicit function?
Implicit functions definition is not direct and
What? Anirudh, is it Anirudh? Who is it? Siddhant. No.
yes, Anirudh only.
Anirudh, go ahead. Your volume is a bit low. What is an implicit function? Hi, are you there? Okay, so y of f of x, the function defined as okay, so the function defined as y equal to f of x is called an explicit function. Function defined as f of x comma y equal to 0 is called an implicit function. It's an implicit form. Function represented in implicit form. You cannot separate x and y variables easily, right? So when you do that, you can use numerical techniques to plot the function, right? It's not very straightforward to plot it. So this is a website which will let you plot it online because it's very easy to plot eigenvalues. Usually the null functions will be of the form f of x comma y equal to 0. So that's an implicit form. Okay, so let us look at just play around with it a little bit. I'm taking two functions, y equal to x comma x minus x cube and x equal to y minus y cube. So the okay, so y equal to x minus x cube looks like this. X equal to y minus y cube looks like this. If you plot them simultaneously, you see that they're intersecting at 3 points here, here, and here. So now if you change the parameters of the function, let us say I want to add some point to, okay, it moved a little bit. The fixed points change a little bit, but you still have 3 fixed points. Make it 0.5, move even more, still you have 3 fixed points. Make it 1, right, still you have 3 fixed points. 2, 1. So somewhere at 1 point and 1.2, 1.5, yeah, 1.6. It is j. So what's happening? You can see here at 1.5. At this, maybe I'll make it 1. At 1.4, you have 2 fixed points here which are very close. Right, other fellow is a bit far, but you increase it a little bit. 1.5 closer, 1.6 even closer. You see there, the 2 fixed points are coming together. At 1.7, it's gone. The 2 fixed points have disappeared. Kind of, they smashed into each other and just got annihilated. They disappeared. And now you have only 1 fixed point. If you go to 1.8, there's only 1 fixed point. You can imagine that when that happens, the dynamics of the system would have changed quite drastically with just that little change, right? Because when you have 3 fixed points, you can imagine more complicated flow. Okay, so you can play with this system, and so here is your familiar circle, right? And you can get more complicated stuff here. So we'll also look at other examples later. I just want you to play with this plotter, right, and plot some implicit functions and see how it looks.